Okay, so welcome everyone to the Culture Seminar Online, and today our speaker will be Johann Mitteramskogler from Linz, and he'll talk about simple general solutions of first-order algebraic ordinary differential equations. Johann, please.
Thank you. What a title! It's very long again, as are usually my titles. Thank you very much, Gleb, for the invitation to speak at the coaching seminar. And for those that don't know me yet, I am a PhD student at the Johannes Kepler University of Linz in Austria. And I'm studying at the Research Institute for Symbolic Computation under the supervision of Professor Franz Winkler. And since so many people have put some nice pictures of the universities on the title slide, I also included one. So this is Hagenberg Castle. It's not located at the JKU campus. It's 20 kilometers or so away, roughly 20 minutes by car. And I'm a bit cheating. This picture was taken in autumn. Right now it's very grayish there. And just let me test if my pen still works. Oh yes, so if you extend the glass like this, then here would be my office window. Right. Very good. Everything seems to work. Let's get on. So I want to talk today about a very simple kind of general solution of an algebraic ODE that you might want to construct, and simple in an somewhat overloaded sense. But we'll come to this in a minute. First, I would like to speak about a bit of the background about the development of these type of algorithms that will go into the direction that I will present today. Just to give you a bit of background knowledge of what we do and how this developed, just very briefly. And for this introduction, I'll be a bit sloppy. It will be more rigorous later. And for now, we will just say that F is an algebraically closed field of characteristic 0. And we'll just consider, for now, derivations d by dx. So the usual derivation you'll find. And I will say that a first-order algebraic ODE, if you like it in the definition that is usually given in analysis or calculus books, then it's an ODE of this implicit form, a function of x, y, and y prime, so first order. And when I say it's algebraic, I mean that this function f is actually a polynomial, and degree of v is at least 1, means of course that y prime actually appears in this differential equation. Otherwise, it wouldn't be first order. And typically, I will assume that f is irreducible for constructing solutions. I mean, if it's not irreducible, just factor it and consider the solutions of each individual factor. And what has been done before, or what I've been doing when I started my PhD, I have been looking at algorithms for constructing so-called rational general solutions. And these are just solutions of such ODEs which are rational in the independent variable x. And the coefficients here, these are just constants in some extension field of f. You know that when you are looking for a general solution, you have these integration constants for first order. You will typically see 1, which might appear also rationally, or it might appear as a root somewhere, but you would have to extend your field. You need at least some integration constant. And for first order, you need precisely 1 integration constant to construct a general solution. And here I have an example of a very simple type of ODE that I will consider. So it's polynomial. Typically non-linear, of course. As I said, it's a polynomial relation. It's not linear, and a typical or a rational general solution would be, for example, here 1 over c squared minus x squared times c. All right. So when did this actually start? So we at the Research Institute for Symbolic Computation, we started into this constructing solutions of differential equation business at least more than 12 years ago. And basically this started after a paper by Feng and Gao, where they used the kind of techniques that we were developing here previously. And they, in this paper, it's from 2004, the first, and 2006, the second. And they studied a very simple kind of differential equation, a first order autonomous one, which means the x doesn't appear in the differential equation, and with coefficients just in Q. And they had a very neat idea for constructing a general solution. First, they would look for a non-trivial rational solution, which means a solution where the x appears in y hat. And then they showed that if you just take the solution and shift the x by this integration constant c, by this arbitrary constant, then you'll get a rational general solution. And this is a very neat trick and a very nice way to construct these solutions. And well, it works only for autonomous ODEs. It doesn't work. It works no longer for non-autonomous ones. And initially they computed this non-trivial solution by a rational parameterization, which they later swapped for Paddy approximations, which is computationally more efficient. But this was sort of the paper that got us interested in this research field. And this approach then was generalized in 2010 and 2011 by Johann Mitteramskogler to non-autonomous first-order algebraic ODEs. And this algorithm, yeah, it worked in the general case, and it extended more or less directly the approach by Feng and Gao. Although from a differential perspective, it's a bit weird what they did. But I don't want to go into detail on this. I'll want to go to the last algorithm before I go into my research, and just that we are all on even ground. Again, what is a rational parameterization, or what do I understand by a rational parameterization? For an algebraic curve, this is just a dominant rational map from the affine line to the curve. And by a dominant rational map, I mean a rational map, so given by a tuple of rational functions, such that the image will be Zariski dense in the curve. And we say that a rational parameterization is proper when it has a rational inverse. So this is the classical definition you'll find in algebraic geometry. And for an algebraic curve, which has a rational parameterization, we usually say that the curve is rational. Not typically you would distinguish it between unirationality and stuff like this, but for curves, this is the same.
May I ask a question about the previous slide?
The previous one, yes.
Right. So in number 2, you're just saying that y hat of x plus c, that family is just solutions, right? You're not saying that all other rational solutions are of this form.
The general solution. Note that there could be singular solutions which are not of this form, or which cannot be obtained in this way. Yes.
But could there be another general solution family of a different degree?
Of different degree? You mean in the degree of the rational function in X?
Yeah.
Or?
Yeah.
So they construct this solution from a proper rational parametrization. For these, we know what the degrees look like. So in this sense, I don't think so. That's
okay. So this is saying that every general solution looks like this.
Well, in principle.
So this is saying that find a non-trivial. Is the saying that for every y hat you have this family? So this is what it's saying, right? But does it say that every family can be constructed from one particular? So are there different families? Are there different families?
Well, they would have been differentially isomorphic if there were any other. So with this respect, no, there are no other.
There is just one. There is just one family, you're saying.
Well, you can slightly represent them a bit differently. You can shift by another constant or a plus two, so on. So it will look slightly different, but in principle it's the same, and you should obtain each particular solution in such a way that you specialize this constant to something.
All right, thank you.
You're welcome. I'm sorry, I'm a bit hoarse. If my voice drops below the audible threshold, please interrupt me and I will raise it again. Okay, let me just check the time. We're approaching pretty fast. So the last approach, I will jump better to the example directly and then look at the algorithm. So the last one, it uses a pretty neat idea. So if you have such an algebraic ODE, so this was a polynomial in f, y prime, and y, you might think about this polynomial only as a bivariate polynomial over f of x. So rational functions in x, and you consider this then as a polynomial which generates an affine plane curve. Now, and if you can find a rational parametrization of this curve, then you're able to sort of reduce this differential equation that you have to a quasi-linear differential equation, well, actually either a linear or a Riccati equation, such that the rational general solutions of these correspond, and you can transform the rational general solutions via the rational parametrization into each other. And I indicated this here briefly. So for this equation, you have this proper rational parametrization, where this C here is my parameter. And I'll again, what I want to find here is then a G, which transforms my parameterization such that the derivative of the first component is equal to the second. And what this does is it mimics somehow how a solution would behave in the equation. And it turns out that in this way, when you can find such a transformation, that you can actually construct a general solution. And to find this G, you have to solve this quasi-linear differential equation, which actually has to be Riccati or linear. I will jump directly to the algorithm before I lose too much time. So this is an algorithm from 2008, and it works in this way. So you plug in a first order ODE, so an algebraic ODE, which should be absolutely irreducible as a polynomial in f of x. So, which means irreducible over the algebraic closure of f of x. And then you construct, if your curve has genus 0, if it's a rational curve, you construct a proper rational parameterization of this form. And then you build from this transformation. You can build from this by taking derivatives with respect to x, with respect to the parameter. You construct from this then this quantity, which will be in general a quasi-linear differential equation then. And there they use then some knowledge from other papers, like Kovacic's paper, where they said, well, such an equation can only have rational general solutions if it is either Riccati or linear, which means that we can reduce to this case here, and then we have to find this G hat, this transformation, which turns the first component of the parameterization into the derivative of the second. This then has to solve either a linear or a quasi or a Riccati equation, and for this there exists an algorithm that can do this. The algorithm, so in general, to find all rational solutions of such an equation, this has been considered in Kovacic's paper, where he studied the linear second order differential equations. There's also an algorithm for this problem in there. And this has been adapted by other authors that will look only for rational general solutions. So every step in here is actually algorithmic, and we can use this algorithm to really decide whether such a first order differential equation has a rational general solution of not the most general type. So we don't allow, for example, roots of our integration constant here. We allow only those rational general solutions where the C appears rationally. All right, so much for the introduction. And what I will show you today is that we can actually generalize this type of algorithm. So the type of algorithm that you will see at the end will look almost the same as this, but we can generalize quite a bit, and I'll use a slightly different perspective, slightly less geometrical view, and not transforming solutions via parameterizations to the line, and consider how they look there and transforming back. But the type of algorithm I will consider will be very similar to this one. And what I will also do is, and what has been done in all these approaches, is that I have some differential base field over which my algebraic ODEs are defined. And I will look for solutions that can be constructed by just adding one single arbitrary constant to this field. And that will be the topic of my talk. But before I will delve into this, let me just make all these notions a bit more rigorous and not as sloppy as it has been for this introduction. Just that we really know what we're all speaking about. So for the remainder of the slides, I let K be an ordinary differential field of characteristic 0. which has attached to it the derivation delta. And by U, I will consider a universal differential extension field of K. So this is a field that is basically large enough that it will contain all the solutions, the general solutions which we could imagine or ever need here. I don't have to work really with this field. It's just for convenience that I don't have to specify where exactly my solutions live. But typically such a field is one way you find for every prime differential ideal a generic zero if it's a consistent system from which this arises. And to save a bit of typing, I'll usually substitute the word differential by the letter delta and just speak about delta fields and delta polynomials, stuff like this. And I will typically denote the nth derivative of an expression by E sub in parentheses n. And the zeroth derivation is just the expression E itself. All right, since we are doing differential algebra, we have a very neat way of really characterizing what we mean by a general solution. And this is something that is known by everybody who has studied differential algebra. So if I should skip this, just tell me, otherwise I will walk through it briefly. So if you take a differential polynomial in the very simple differential polynomial algebra over my delta field K in just one delta indeterminate Y, and I consider now such a differential polynomial of order 1, which I assume to be irreducible, meaning irreducible as a polynomial over K. Then there is, similar to the case of commutative algebra, where we can decompose a radical ideal into the intersection of a number of prime ideals. We have the same here in differential algebra, where the radical differential ideal generated by F, which I denote by curly brackets F, this can be decomposed into this component. So the radical, the colon ideal of the radical with respect to the separand, or if you want to see it differently, you just saturate the differential ideal generated by F by the separand, and possibly some other components which will be not of interest for me. These other components, these will all contain the separand, and I'll be interested just in this first component, which does not contain the separand. And this component is called the general component of F, and it is the essential prime divisor, the unique essential prime divisor that does not contain the separand. And we'll use this prime differential ideal to define what the general solution of an AOD is. And since it's prime, it will have a generic zero in my universal differential field U. So what is now, from now on, an algebraic ODE of order 1? Well, it's just an equation of the form F is equal to 0, where F is a differential polynomial of order 1, coefficients in my favorite differential field K. And by a generic zero of this differential equation F equals 0, I mean a generic zero of the general component of F. And from now on, I will again assume that my defining differential polynomials of my algebraic ODEs are irreducible, just for convenience. Okay. As I said, I have I favor a bit of a different view what actually a rational parameterization is. And to make this not too lengthy, I'll typically take the the approach from field theory, where I say, well, such a rational parameterization, it's actually a generic point given by rational functions, and a rational curve is one whose function field is just a simple transcendental extension of K. In a nutshell, it's written more elaborately here, and I will also consider curves, K curves, which are not necessarily over an algebraically closed field. So the coefficients are not a priori in an algebraically closed field. You will see later why I want to do this. But I will, for such a thing which is defined over K, I will call a K curve. And a K curve is always defined by bivariate polynomial, which is irreducible over K and non-trivial. Yes, and finally, a parameterization, as we had it before, it's such that, again, this image here of the rational functions is Zariski dense in C. And by a proper rational parameterization, I mean one such that these two components of the parameterization actually give me K of T. So they don't generate an isomorphic subfield, they really give me K of T. And what do I know about proper rational parameterizations? That's something very important, actually. So if we have a proper rational parameterization of a curve, it's first of all not unique. There are many of them, but they are all related via K automorphisms of K of T, which are just Möbius transformations. So if you have one proper rational parameterization and a different one, you can substitute the parameter T with a linear rational function with the coefficients in K, such that you will get the other. And this will be very important for the remainder of the talk, this property. And now finally to my actual aim and goal of the talk. And for this, I will let C be an arbitrary constant over K, which is contained in my universal differential field. By an arbitrary constant, I mean just a constant, which means delta of C is equal to 0, which is transcendental over K. And my goal is now, so if I've given a first order algebraic ODE, f equals 0, I want to determine if there is a general solution, which means a generic 0 of the general component of f, which is contained in this very simple differential extension field. Well, it's almost, it is actually just the usual rational function field. By these angular brackets, I mean the differential field generated by joining this C. But since C is a constant, this is just the rational function field with coefficients in K as a field. Okay, and this is what I want. And before we go on, one way to think about this defining differential polynomial f, so which defines my algebraic ODE. Well, you can think about this actually as a bivariate polynomial in y0 and y1. So this is y and delta y. And you forget about this differential aspect for a moment. You just view it as a bivariate polynomial in two variables in over the field K. And this will give you actually a K curve in the affine plane over U. And we'll denote this by CF. And we'll see that actually we can get a general solution of this differential equation by a special generic point of this curve CF. But first, let me just say a couple of very obvious observations which we can take at the beginning. So if you have such an AOD, and this has actually such a very simple general solution, so one that can be constructed by joining an arbitrary constant to k, then this delta polynomial must be absolutely irreducible. Now this follows since in this case, this function field, actually the differential function field, this will be just a purely transcendental extension of k, which means a regular extension. And by methods of field theory, we know then that f must be absolutely irreducible. The second is that this solution y hat, well, this actually gives me a rational parameterization, where I view this arbitrary constant c now as the parameter. But this tuple y hat, delta y hat, this will actually vanish on the polynomial f, and it will give me a rational parameterization. And this, of course, means that, well, whenever I have such a solution, then this curve CF must have genus 0. So much now for the basic observations. Now, one might ask then, okay, so if I have such a solution, which will give me a rational parameterization, this will give me a rational parameterization, but can I actually find one that will give me a proper rational parameterization? And the answer is yes, indeed. This can be done and this can be shown. And this now gives us a very powerful tool to attack this problem. Because if such a solution exists, then there exists one which gives me a proper rational parameterization. Well, but then I can just compute any proper rational parameterization of this curve CF and try to obtain a solution via a Möbius transformation, which we know that all proper rational parameterizations of the same curve are related by. So I can more or less break it down to parameterizing this curve and then trying to find just a linear rational function, such the result will then solve my differential equation as well. And this is the basic approach, how we attack this problem. I'll have not the time to go into the proof here. But one thing that I just want to mention is by this very nice property, I will get also nice degree conditions. There are also similar degree conditions on this very first algorithm for rational general solutions that I mentioned. There's also a similar degree condition in there, which I have here. And this comes from the fact that all proper rational parameterizations have very precise conditions what their degrees must look like. So if you have such a parameterization, then you know that the degree in the parameter t of the first component must be equal to the degree of your polynomial in B and vice versa. The degree of the second component in T must be equal to the degree of F in the variable U. And by this, it is actually very easy to derive this condition, this necessary condition, that you cannot possibly hope to find such a general solution in K adjoint C. If your differential polynomial has degree in Y, which is strictly greater than 2 times the degree of your defining polynomial in delta Y. And by this, I come to the algorithm. And as I promised, this algorithm, if you take now all together, which I've said and a bit more, just to mention, all this is based on a paper that has been submitted, and we are still waiting the reviewers course. But the preprint is available online, and I have put it into the literature. If you're interested in the details, you can look the paper up, so the preprint up. And here is now the algorithm for finding such a general solution in, well, K adjoined by just one arbitrary constant C. And it looks almost the same as the algorithm that I presented at the end of the introduction. So as well, F must be absolutely irreducible. This curve, which we obtain from F, must have genus 0. Here now these degree conditions, they are definitely new. They were not present in the previous algorithm. And this step here, this is also, well, kind of new. It depends a bit on the field you are looking at. Apart from this, it's not very interesting. And the other conditions, well, this is also pretty similar to the algorithm before, except that we have to change d by dx by our generic derivation delta now. And here we have also a very similar condition as before. So this is also basically a Riccati equation or a linear equation that we have to solve. But now we know precisely what we are looking for. We are looking for linear rational functions of this form, which are Möbius transformations, which means they are the determinant of this must be non-zero, which solves this equation. And if we can do so, well, we just plug it into the first part of our parameterization, and then this will actually give me a general solution of the original AOD. And just to see that this really works, is here an example where you can see that, well, we can actually do a bit more with this kind of approach than before. And we choose here this differential field K just to be the algebraic closure of the complex rational functions in X. And consider this differential equation. Now this we can parameterize. The parameterization looks just like this. Then we construct this quantity F and check if it is linear or a Riccati equation. And in this, with respect to C, and this is the case, then we might try to find this linear rational function G hat. And this is just given here by this very easy polynomial. And we plug this into our parameterization, and we take the first component of this, and this will actually give me a general solution of the original AOD. And we can also do this for other fields. For example, if you like Liouville general solutions, and it works just as before, but you choose a different field. K is now, well, you adjoin e to the x. And actually the choice of this field, it doesn't influence the parameterization much. So the parameterization is, for this step, you will need just the smallest field over which your polynomial is defined, and might have to extend quadratically at most. But here, for example, you see this is an autonomous differential equation, and the parameterization you get does not contain any exponential functions or stuff like this. This is actually then really needed when finding these linear rational functions. There we have to actually use the whole space of functions when we are looking for solutions. Okay, I hope that this was not too quick. I will save the open question maybe for the discussion afterwards. And thank you for your attention. If you have questions, please ask.
Thank you, Johann. So yeah, please, we have some time for quick questions, and more elaborate questions can be postponed to after the breakout rooms. So if you have a question, you can either type it into the chat or just unmute yourself and ask.
So I have a question. So here you took in the previous example, you took the base field as adjoining the exponential function. What is there a sort of a kind of extension that you cannot deal with? So for example, what is it? Is it important to choose the exponential function here, or
so in this example, I chose it because I knew that the solution requires an exponential function.
I see.
So, well, actually, you can look at this procedure from different perspectives. You can always try to parameterize, and this will just be basically the coefficient field of your polynomial, at most a degree 2 extension, and then where you really need a possibly very large extension field is then by solving this linear Riccati equation. There you have to actually see what solutions you actually need. In the way that I have stated it here, it's from a, how should I say, from a theoretical perspective, very nice. You just agree a priori in what type of solutions you are interested. And then in the second step, this will be actually the step where you need this possibly large solution spaces.
Thanks.
But solutions which I cannot deal with, well, the most basic solutions that I cannot deal with are those where this integration constant appears in a root or something like this. This is something I cannot deal with in this approach. So my ODEs, or the curves that they generate, they must be rational, and this is precisely the case when I just consider these integration constants adjoint rationally. And one step that's, I mean, the algorithm for the rational case, this was really algorithmic. And here I have one problem in the sense that this second step here, there I'm not sure how algorithmic this is. It might be for certain solution classes. As I said in the beginning, for rational, there's something in Kovacic which you can use. I don't know if this is the case for, let's say, algebraic solutions. The parameterization step, this is fine. Even this slightly special parameterizations which I deal here, where I don't extend k, this is fine. For this, there exist algorithms, and they've been published, and this is algorithmic. The only this second step where I have to find g hat. This can be problematic, and if you can solve this will depend on your field k, or if you can solve this algorithmically.
There's a question in the chat from William Seed about the examples.
So let's see, these examples I think I took from the book of Kanke. If you go to the paper, I think I have even written down the equation number. But these two I have from Kanke. Yes, first they were nice examples because I knew what solution types I'm looking for, and to verify if I will actually get these solutions or something horribly complicated.
I have one more question.
Yes.
Where do you use the degree condition in your algorithm from line 2 to line 10?
The degree condition, this is a necessary condition. Here, it's at the top. Oh, you mean the examples? Oh, the examples they fulfill the degree condition. No problem. But this is just to the 2018 paper. This is just one additional necessary condition, which your differential equation has to satisfy. Otherwise, there cannot exist a solution of this type. But it's only a necessary condition. It's not far from sufficient. And the examples satisfy.
Does that mean line 2 until line 10 still work if we don't have that necessary condition, right?
Yes. If this one is not fulfilled, then you can just quit. You don't have to compute parameterizations. You cannot obtain a solution in this case. And this is also one thing that actually extends this decision algorithm from 2018. The condition was not there yet. And yes, it's one nice improvement. And if you look at the paper from Feng and Gao, they also have precisely this bound there, and they have another bound, but this depends on their field. I cannot have this other bound that they proposed, but it's the same bound that Feng and Gao actually, or one part of the same bound that Feng and Gao proposed.
I have one other question. In line 7 in your algorithm,
yes.
How do you know that the hat must be of that form? That means degree 1 in the constancy. Why not degree 2?
Well, actually, we knew this basically for the decision algorithm also. I think it was in the book of Schwarz, where he described how the solutions look like. But if your linear or Riccati equation has such a strong, as we called it, a strong rational general solution, then it has one which is of degree 1 in C also. And how I know this here? Well, actually, I analyzed how these linear rational functions or their derivatives must look like, and this is something I'll come to after the breakout rooms. So we might discuss this also there, and then you'll see how I got there.
Thank you.
You're welcome.
Okay, good. So then let's proceed to the breakout rooms. Ronnie will